Welcome to section 3.4 where we'll be talking about sets. So again, pause often and we're going to be clicking out of the video to play some different games. So question of the day, what makes a grouping of items a collection? So go ahead and press pause, write down what you think makes up a collection. So we're going to be talking about sets, and there's a very fun game called Set, and I encourage you to go to either of these two and play for a little while. If you want to wait till after I explain it, or if you want to figure it out, go for it, but pause here and go play some games. So the game of Set has these different shapes, and they have different shapes, different numbers, different colors, and different fill. And so how you play the game is you create a set of 3 cards, and each card has those 4 different features. And what you do is a set is in which the 4 features looked at one by one are all the same or all different. So in other words, for the 3 cards, all the shapes are the same or all the shapes are different. The color, all this color is the same or all the color is different. The number of items is the same or all different. The shading is the same or all different. So let's take a look. This is a set because. All right, let's start with the shape. So I have a squiggle, oval, diamond. They're all different. Remember, they can be all the same or all different. Let's talk about the color. The color is all different. What about the number of items? 1, 2, 3, all different. What about the shading? They're all striped. They're all the same. Now, this would not be a set if this card was red. Why? Because the color would be 2 are the same. And remember, it has to be all the same and all different. So let's explain why each of these are sets. Now you can pause it and try it by yourself, or you can do it with me. So let's look at the shape. The shape, all the same. The color, all the same. The number of items, they're all 2, all the same. But the shading is all different. Let's look at this one. The shape, they're all different shapes. Squiggles, diamonds. The color, they're all different color. The shading, they're all different shading. And the number, 1, 2, 3, they're all different. So these are all sets for different reasons. So pause here, and you can play with this here. There are 6 sets in here, or you can go play again with these links and see if you can find all 6 sets. And it's okay if you can't, but I'm going to put the answers on the next slide, so make sure you're ready to see that. So there you go, and that's the reason why. So again, I encourage you to play here and think about sets as we continue on. So a set is a collection of objects, and collections could be coin collections. They can be things that are all the same, things that are all different, right? And the empty set is the set that contains nothing. And the empty set is actually a part of every other set. And a subset is a set within a set. So it's like a bunch of different vocabulary there. But let's think about this. What are some possible sub-collections of this set? So we could say, okay, these are the suits of cards. So that's a sub-collection. We could say black cards, right? That would be the spades. Oh boy, I'm just going to write spades and clubs. Spades and clubs. The red cards are hearts and diamonds. So those are some sub-collections of that. Now maybe you know the cards really well. You could say even cards, odd cards, face cards, right? There's lots of different sub-collections, but if we just look at these 4 items here, those would be some sub-collections. The sub-collections are subsets. So if we wanted to list every subset here, all right, let's do it. So I'm just going to call this spade, heart, diamond, and club so that it's a little bit easier for me. So all of the subsets, first I could separate them by 1, right? Each is its own subset. Then I could go through and go by 2, S, H. All right, now S, D. This is a good systematic way. S, C. And then, okay, H was already with S, so H, D, H, C, DC. Okay, those are all the 2s. Let's look at 3s. SHD, SHC, HDC. SHD, SHC. Oh, I missed one of those S's. SHD, SHC, SDC, HDC. And then 4, all 4. Now there's one set missing here, and that's the empty set. It's a part of every set. So how many subsets are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I had 4 items, 4 elements, and I have 16 subsets. And here they are with their actual pictures, if that's helpful. All right, what about creating a list of all the subsets of this? So, okay, it could be all 3, HTD. I could go into sets of 2, HD, TD, sets of 1, H, T, D, and then don't forget the empty. So there's 1, 2, 3, 4, 5, 6, 7, 8. So we had 3 elements and 8 subsets. So when we create a subset, it's basically saying, is it in it or is it not in it? So for each of these, I want you to actually predict how many subsets they will be in each set. And then check your first predict, then create the list, and then see if you can find a pattern. Press play when you're ready to see the answer. So here it's going to be 4 subsets, 8, and 16. Well, let's see if we can find a pattern together. So we had these 3 sets. Now the number of elements, Mac, PC, Smile, whatever, 3, 4. And now the number of subsets. So 2 elements, 4, 3 elements, 8, 4 elements, 16. Do you see a pattern here? 4, 8, 16. See if you can predict for 5, 6, 7, and then N numbers. So pause it here, really try, puzzle it out, and press play when you're ready to see the solution. So if I notice this, I can see that this is clearly doubling. But the problem is that that's not telling me about N. I need to find a relationship between the number of elements and the outcome. Well, 2 times 2 is 4, but 3 times 2 is not 8. What about using the power? 2 to the 2nd power. This is 2 to the 3rd power. This is 2 to the 4th power. I wonder what if 32, let's see, 2 to the 5th power is 32. So I can actually determine the number of subsets by taking 2 to the number of elements. So this would be 2 to the 7. So a set containing n elements has 2 to the n subsets. And the power set is the set that contains all the subsets of the set. And that concludes section 3.4.